Welcome to this lecture series in real analysis. In this lecture, what we are going to do in this lecture, we will be looking at sums and products of continuous functions, I think, So let's recall some relevant things. So we have discussed the definition of continuity, and then we discussed various equivalent criterions. We discussed the epsilon delta criterion, the criterion via neighborhoods, and for this lecture, we will be using the criterion via convergence. What does it say? It says that suppose we have a function from a set S to reals, where S is a subset of reals, and x0 is a point in the domain. Let me write that again. So f is some function, and x0 is given in S. Then S is continuous at x0 if and only if whenever we choose a sequence in S such that the sequence converges to x0, then fxn converges to fx0. So we discussed this at length in the previous lecture. And let us recall some facts about algebra of convergence which we will use. So if we have two convergent sequences, then the summed sequence also converges, and it converges to the sum of the limits of the individual sequences. Similarly, the scaled sequence converges to the scale of the limit, and the product sequence converges to the product of the limits. So we know this, and a similar theorem holds for inverted sequences. So fix a real sequence, then the inverted sequence, fix a convergent real sequence, then the inverted sequence also converges, provided everything here makes sense. So xn shouldn't be 0 for any n, only then you can talk about 1 by xn. And the limit of xn is non-zero, so that one can talk about 1 divided by the limit. So when these two conditions hold, this is also convergent, and it converges to what? Converges to 1 upon what the original sequence converged to. So keep in mind these two facts, and with that, let us proceed. Here are some problems for practice. And now let us get started. So first we will discuss sums, products, and scaling of continuous functions, and then we will later talk about the inversion of a continuous function. So fix two continuous functions f and g on a subset S of R, of course non-empty, and fix a point x0 in S, x0 in S, such that f and g are both continuous at that point. Then the summed function is also continuous at that point, the product function also continuous at that point, and the scaled function for any a in R, we can define the scaled function. This is also continuous at x0. To be very clear, what does this mean? This is a function which takes a point x in S and outputs this value, and similarly these two. So let's argue why the first one is true and the second and third one will be very similar. Okay, so we need to prove that this is continuous at x0. So by the convergence criterion of continuity, we choose a sequence. We choose a sequence xn in the domain of the function such that xn converges to x0. But we know that this happens. Why? Because f is continuous at x0. F is continuous at x0, So we have that, and similarly for g. And now by what we recalled, the algebra of convergence, this implies that this is the case, which is same as saying that the summed function, or the sum of f and g, has this property, right? So, and therefore f plus g is continuous. So that's it. It's continuous at x0. So a straightforward consequence of the algebra of convergence that we discussed in the beginning of this lecture Okay. So similarly, you can prove this and you can prove that one. But I encourage you to prove this thing using the epsilon delta criterion. Don't use the algebra of convergence. Prove the same thing using the epsilon delta criterion. That's a good exercise. Okay. Let's move on. So let's see some examples. So fix a natural number n and define this function f via this recipe. Just take the nth power of the input and we want to show that this is continuous. So we will do this inductively. Clear for n equals 1, we have discussed this. Because for n equals 1, this function is just x going to x. And you can prove this is continuous using whatever you want. The most simplest one is using the criterion via convergence. Okay, so n equals 1 is clear, and for n equals 2, what do? You take, so suppose you have some positive n, let's keep n as unfixed. So n is just some natural number. Define f as above and g as the identity function. Okay. So f is defined via this, and we define our own function g via this recipe. So g is clearly continuous because it is, of course, the identity function, or you could say it corresponds to the n equals 1 case. So g is the identity function and hence continuous everywhere. But what is fg? The product. Fg takes little x to fx times gx, which is x to the n times x, which is that thing, right? But by what we discussed, the algebra of continuity or whatever, since f and g are continuous at every point, fg will also be continuous. So what are we doing? We are arguing via induction. We know the statement is true, or yeah, I didn't write the statement, but the statement was that f is continuous. Continuous everywhere. So clear for n equals 1, because for n equals 1 this was identity. Now suppose we have already proven that f is continuous for some n. We have proven the base case of the induction, which is n equals 1, but suppose now for some n the statement is true, and now you define your own g, which is of course continuous. Then the product function will also be continuous, but the product function corresponds to a higher value of n, the next higher value of n. So that's reasoning via induction. If you don't like it, just go step by step. N equals 1 you have done. Now take f as identity, g as identity, then this function is just the squared function, and hence the squared function is continuous. Then take f as the squared function, g as the identity, then this is the cubed function, and so on. That is what induction is all about anyway. Okay, so the nth power functions are continuous. All right, and this actually makes it very easy. Previously, we did these things. I don't know how we did it. Yeah, I don't think we even stated it previously. This is the first time we are stating that this function is continuous. Anyway, and now for a little bit of a generalization of the previous one, you fix n real numbers, or n plus 1 real numbers, and define this function which takes x to a0 plus a1 times x plus a2 times x squared plus dot 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 an times x to the n. Such functions are called polynomial functions, and we want to say that these are also continuous everywhere. So define for each k in the function, I wanted this to be different colored, the function gk as x going to x to the power k. So gk is continuous by the previous example, and now f is what? The function f is nothing but the constant plus a1 g1 plus a2 g2 an gn. Now Look at this. This is just a constant added to everything. So this let's ignore for the moment. G1 is a continuous function and we are scaling it, and we saw that scales of continuous functions are continuous. Since G1 is continuous at every point, its scale is also going to be continuous at every point, and hence this is a continuous function. Similarly, A2, G2 is a continuous function, and so on. So the constant function, and then this function, and then this function, all of these are continuous functions, and we have just added them, and we have seen that sums of continuous functions are continuous. So therefore, f is a continuous function. So all we are doing is we are writing f as sums of continuous functions. This is an n-fold sum, but once you have proven that sum of two continuous functions is continuous, the same thing also holds for sum of any number of continuous functions, as long as the sum is finite. Okay, so f is continuous, and again, see, if you try to prove this via the epsilon delta criterion, it will be quite a lot of headache. But with our machinery, little bit of machinery, this is so simple. Okay, so polynomial functions are continuous is our takeaway from this. All right. Okay, so now we will talk about composition of two continuous functions. So fix a function from S to R, schematically represented this way. We'll come to this diagram. So f is a function from S to R and g is a function from T to R, such that the image of S under f, that is the image of f, is contained in the domain of G. Now the domain of G is represented this way. That is the set T, and it takes the function G takes it to real numbers. And f is a function whose domain is S, but its image is contained in the domain of G. So this is one way to diagrammatically represent it. Each point of S is taken inside the domain of G under f, and then G does what it does. Okay, so fix a point x0 in the domain of the function f, and assume x0 is such that f is continuous at x0 and g is continuous at fx0. So we have a point in S where f is continuous, you take the image, and g is continuous here, and then naturally we want to prove that the composite function is continuous at x0. So recall, the composite function is just the function which picks a point in S, applies f, and then applies g. That's the composite function, and we want to prove that it is continuous at x0. Again, this is straightforward using the convergence criterion. So let xn be a sequence in S such that xn converges to x0. We want to show that this is the case. Right? Okay, so why is this? Well, we know two things. We know that this happens because f is continuous at x0. And now this is a point in the domain of G, and this is a sequence in the domain of G converging to that point. Each fxn is in T because image of f is contained in T. So this is a sequence converging to this is a sequence in the domain of G converging to a point in the domain of G, and G is continuous at that point. We are given that G is continuous at that point. Therefore, by the continuity of G at that point, we have this happens, and hence I had written something completely wrong upstairs. That was meaningless. That's what we wanted. Yeah. So we have, sorry for the repeated typos. So first we had this, and then we applied G to obtain this convergence. And this thing is same as that thing, which is what we wanted to show. Okay. So that proves that if we have two functions f and g which are composable, meaning the image of f is contained in the domain of G, and you have a point x0 in the domain of f such that f is continuous there and G is continuous at the image of that point, then the composite is also continuous at the original point. So if f and g were both continuous functions and they were composable, then the composite would also be a continuous function. Okay. So now we can proceed. And here is some very simple example. Suppose we have a function f which is continuous everywhere, and we define this new function g as follows. Gx is absolute value of fx for all points in S. Then we want to say that g is also continuous. And why is that? Just think of it as a composite. We have S going into all reals, and then we have the absolute value function, which we know is continuous. F is continuous by hypothesis. This is continuous because we have proven it previously. And this composite is precisely what G is. And therefore, G is continuous because it is the composite of two continuous functions. Similarly, here we have a function f which is continuous, given to be continuous. And we have another function g defined as gx is the nth power of fx. Then we want to say that g is continuous. And the reason is the same, just express this thing as a composite. We have the function f, and then we have the nth power function, which we just proved is continuous. So this composite is precisely the function g, and hence g is continuous. Okay. Now we want to talk about inverting a continuous function. So first we have a small lemma. Define this function which takes a non-zero real number to 1 by x. So the domain of this function is all non-zero reals. Okay, so that's the definition of the function. And we want to show that f is continuous. And I've drawn the graph of the function for the positive reals. For the negative reals, it will be similar, something like that. So for the positive reals, it looks something like this. And we want to show that this is continuous. But this again follows immediately from the algebra of convergence we recalled earlier. So fix a sequence. Let xn be a sequence in the domain of the function, which converges to a chosen point x0. So before even writing this, I should have written choose a point x0 arbitrarily in the domain. All right. And now suppose we have a sequence in the domain which converges to x0. We want to show that, to prove continuity of f at that point, we want to show that this is the case, but that is same as saying this is the case, but by what we recalled, this is true. Xn is a sequence such that none of the entries here are 0, and the limit of the sequence is also non-zero. So the inverted sequence converges to the inverted limit. Okay, so this is what we recalled in the beginning. So this is true, and therefore this is true, and therefore f is continuous at x0. And since x0 was arbitrary, f is continuous everywhere, and therefore f is a continuous function. So the inverted function is continuous. All right. And this is, we'll come to the more general statement, but right now, this is one thing that we should keep in mind. Okay. So now we can prove some corollaries. We have this function g, which is given to be continuous at a point x0 in its domain, and assume gx is non-zero everywhere. Then this inverted function, which is meaningful, because g is non-zero everywhere, this inverted function is a genuine function. What's the definition? It takes a point x to 1 upon gx. And we want to say that it is continuous at the point x0. So again, doing it directly will be cumbersome, but if we just notice that we can express g as a composite of two continuous things, then we will be done. So first we have this function g. Since it doesn't take the value 0 anywhere, g can be written in this way. So g takes s to non-zero reals, and then we apply the inversion function. So g is continuous at x0, and this is continuous everywhere. So the composite is going to be continuous at x0. But what is the composite? The composite is precisely the function 1 upon g. And that's it. That's the proof of the first one. And the second one is two applications of what we discussed. We have a function f, we have a function g, which are both continuous at x naught. G doesn't take the value 0 anywhere. Then this ratio f upon g, which is again well defined, because what is the definition? It takes x to fx upon gx. And we want to say that it is continuous at the point x naught. Again, we already know that 1 upon g is continuous at x naught, and we know that f is continuous at x naught. So the product function is going to be continuous at x naught, but the product of these two functions is precisely that. So these two facts we now know. And yeah, let's proceed if there is more. Yeah, so let's see some examples. We have a function from the punctured reals to reals defined as follows. Fx takes the value 1 upon x minus 2 for all x not equals to 2. So for each point in the domain, this is the recipe via which it is defined. It is well defined because the x is never allowed to be 2. So this is a meaningful thing. And f is continuous because it is basically the inversion of the following function. You take x to x minus 2. And since this never vanishes, the domain is set so that this never vanishes. And therefore the inverted function will also be continuous, but the inverted function is precisely f. So that does it. And this one is also very similar. This time we are taking away 2 points from all of the reals, and then the function is defined via this recipe. This is again well defined because x squared minus 2 will never take the value 0 if x doesn't take these two values. So this is a well-defined function, but this is the product of this polynomial function with that one. And I mean, this polynomial function with the inversion of that one, and both of them are continuous. So this is also a continuous function. Okay, so I'll leave the details to you. This is another example of a continuous function. Okay. And yeah, with that, I want to end this lecture. As usual, like, comment, share, subscribe, and I will see you next time.